guys, welcome to your first homework video for Algebra 2. I hope you guys like this format of watching these short lesson videos at home and really absorbing that content at home. My hopes and dreams are that you will come to class with some specific questions and that you will take the time to watch these videos, re-watch them if you need to, pause, try, start again. And I think that will be helpful in, really absorbing the content more so than just sitting in class and listening to me lecture at the board. I know nobody likes that. So we're going to try something a little bit different. These videos are meant to be quick. They are meant to go along with notes that I have made for you. So the one that we're going to watch today, your first video, is about combinations. We talked about permutations and fundamental counting in class today. And then now we're going to round it out with combinations. This first unit is kind of like a weird mishmash of things, but permutations and combinations is something that I love, so I hope you guys enjoy it. You can see on my screen that I have a copy of the same notes that you have, so we're just going to jump right in and get going with combinations. We talked in class about permutations, so we're going to go ahead and review a little bit with what we talked about in class. Math, as you know, is a cumulative practice. So you really need to do the problems over and over to make sure that they stick, because you're going to use these skills again in other units. You can't learn it, test it, and then forget about it. It's a big old math snowball, and we're going to keep adding to it and adding to it and adding to it. So let's jump right in. We learned that permutations are the number of different ways that events can occur, and that order matters with permutations. Remember, with permutations, you want to think about a list. Combinations is a little bit different because you're thinking about a group. You're thinking about random order. Order does not matter, but permutations, it certainly does. Especially with this first example, like a license plate. If you are in a police chase and you have a specific license plate, the order of those letters matters because they could be chasing the wrong person that didn't commit the crime, because they're, you need to make sure that you've got your specific order of letters on your license plate versus some other order of letters for the person who actually did, rob that bank or whatever you may or may not have done. So how many different license plates can be created if the license plate has 4 letters followed by 2 digits and items can be repeated? So we're going to use fundamental counting for this, which is just one type of permutation solving method. You may remember we're talking about a license plate. We're going to make the little dashes as if we were filling it in. You've got 4 letters. I'm going to put an L here representing letters and then 2 digits. So it's a 6-item license plate, 4 letters, 2 numbers, and items can be repeated. How many letters are in the alphabet? We know from class today and just from our general knowledge of the English language that is 26. So there's 26 possibilities for that first letter. Since items can be repeated, the second, the third, and the fourth spot can all be the same letter. There's 26 different possibilities for every single one of those 4 letters. And then for 2 digits, we're talking about 0 through 9. It's got to be a single digit. So 0 through 9 is actually 10 different possibilities, because 0 counts as 1. And the numbers can repeat. So we just multiply these numbers together. 26 times 26 times 26 times 10 times 10. If you have your calculator in front of you, wonderful. You can use Desmos, which I'm going to show you how to do here. Super simple. 26 times 26, times 26. Why do I keep hitting 25? Times 26 times 10 times 10. Okay, and you get a very large number, 45,697,600. That's a lot. A lot of different license plates out there in the world when items can be repeated. Now, in the contrast, if you can't repeat items, you're still dealing with the 6 different items, 4 letters, and 2 digits. Letter number 1, letter number 2, letter number 3, letter number 4, number 1 and number 2. Okay, so for the first spot, there's 26 potential letters that can be used. But if we cannot repeat items, maybe that first one was an A, well, we can't include A in the number of possible letters for the second spot. So that means we've got 25 possibilities. Maybe this one was a B. Well, then we can't include A or B for the third possibility, so we're going to knock it down to 24, and so on down to 23. Same thing for the letters, for the numbers. We've got 10 potential numbers for that first digit spot. Let's say we use number 1. Well, we can't use number 1 as a possibility for the second, so there's only going to be 9 possibilities. Multiply all these things together. Let's go back to Desmos so we can see. And we are talking about 26 times 25 times 24 times 23 times 10 times 9. And you've got 32,292,000. That's still a ton of different license plate combinations. And if you live in Virginia, which is like the land of 1,000 vanity plates, we're talking about even more combinations. So that is your fundamental counting application for items with repetition and without. A Spanish club is electing a president, a vice president, and a secretary. The club has 9 members who are eligible to hold office. How many different ways can these offices be filled? Okay, so we've got president, VP, and secretary. That's 3 potential offices, and this is a specific order. The president is like the highest, right? The VP is right underneath, and then the secretary is kind of third place, if you will. So we are, again, talking about a permutation. This is a specific order in which these seats can be filled. We know that in our permutation formula, okay, N is the total number of possible events. So the total number in the pool. It's the big number in the problem, if you are ever confused. N is the big number, and R is the little number, but R might not be explicit. You might have to kind of dig into the problem to figure out what your R value is. So in this case, the total number in the pool is 9. It's the big number out here. So we know we've got 9 over 9 minus, what is our R? We are talking about 3 different seats. So 3, which means we've got 9 factorial over 6 factorial. We can expand this out, right? We're talking about 9 times 8 times 7 times 6 times 5 times 4 times 3. Whew, this gets a little tiring. And then the same thing, 6 times 5 times 4 times 3 times 2 times 1. The cool thing about this, you may remember, is that the things that are the same cancel out. So really, in the end, all we're talking about is 9 times 8 times 7. And that's pretty easy to figure out on the calculator. We're just going to type it in as 9 times 8 times 7. So 504. There's another way to do this on the calculator. If you've got a TI-83 or TI-84 or TI-89, I'll show you how to do that as well, but we are really trying to concentrate on Desmos here, guys, because for the SOL, you are going to be encouraged to use this, and next year, you have to use this. So we're kind of making the push for Desmos now, and I would get used to using it because it does some pretty cool things. So if you go over to this Functions button and go up to Stats, which I'm already on, Stats, cool. We are talking about permutations, NPR. Remember that we can express permutations like this, 9 permutation 3, which you can see here, NPR 9P3. This whole experience is really making me realize how bad my handwriting is. I'm really sorry, you guys. So we click the Functions button, we're on the Stats tab, and we're going to click NPR, and into the parentheses over here, first we type our N, which is 9, comma, we type our R, which is 3. You can close the parentheses or not, and you can see you get the same answer, 504. You have 504 different ways that Spanish Club can fill those 3 elected seats with the 9 potential candidates, we can say. Okay? And then last but not least, find the number of distinguishable permutations for the letters in the word. Yellow, Panama, Honolulu, and Mississippi. Remember, we took the total number 1, 2, 3, 4, 5, 6 6 permutation up top, divided by only the things that are repeating. We have 2 L's. That's it. Nothing more than that. So that's what we are going to figure out. We know that if we expanded this out, 6 times 5 times 4 times 3 times 2 times 1 over 2 times 1, well, the 2 and the 1 would wind up canceling out. So all we need to calculate in this case on our calculator would be 6 times 5 times 4 times 3. Don't forget, or don't worry about the 2 or the 1. Oh, wait, hold on. Don't put an equal sign in there, you guys. I know it's counterintuitive. So that equals 360. There's 360 potential permutations for the letters in the word yellow. 360 different ways that you can arrange the letters in that word. What about Panama? So there's 1, 2, 3, 4, 5, 6 letters in Panama. How many letters repeat? The A repeats 3 times. And nothing else. P does not repeat, N does not repeat, and M does not repeat. So we are calculating 6 times 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1. Cancel those bad boys out. It's just 6 times 5 times 4. 6 times 5 is 30. And 30 times 4 is, I hope you said 120. 120. Okay? Honolulu. 1, 2, 3, 4, 5, 6, 7, 8. 8 different letters in Honolulu. And how many are repeating? We've got 2 O's. Cool. And we've got 2 L's. Cool. And we've got 2 U's. So there's no repetition on the H and no repetition on the N. You'll go ahead and plug that into your calculator the same way. You'll do 8 factorial and then 2 times 2 times 2 factorial. And let me change it up and just show you if you've got a TI. Oh, there it is. Hold on. Where are we? There we go. I need to see what I'm putting in here. So we would go to parentheses, 8, and then you go to the math key and go over to probability and hit 4. And that'll give you the little factorial exclamation point. So we're going to do 8 divided by 2 math PRB4 times 2 math PRB4 times, you guessed it, 2 math PRB4. Okay, and that will give us our answer of 5,040 combinations for the letters in the word Honolulu. You can go ahead and do the same thing for Mississippi. How many letters? Ooh, this one's a doozy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. And M does not repeat, but everything else does. I've got 1, 2, 3, 4. S has 1, 2, 3, 4. And P has 1, 2. Okay, so we would type 11 math PRB4 divided by 4 math PRB4. You know, I like to put parentheses around everything just as a precaution. Times 4 math PRB4 times 2 math PRB4. All right, 34,650. It's a lot of different ways that you can rearrange those letters in that word. Okay. So there's a little permutations review for you to refresh what we did in class. Now let's go ahead and move right along to combinations. Combinations is a little bit less pressure because order doesn't matter. There are counting problems out there where order does not matter, like cards. The order that you're dealt cards doesn't matter. You can pick up those cards and rearrange them, but that's not going to change the actual hand that you have. You've got a royal flush no matter which one you get first, second, third, or I guess third. And then you're picking up. Anyways, we're getting into poker now, which we don't need to talk about. So combination, a grouping of objects where order doesn't matter. You've got a little bit of a more complicated formula here, and if you can remember it, great. But honestly, we're at the point now where we can just plug everything right into the calculator. So if our first example is 8 combination 3, if I want to do this on Desmos, I'm going to go back to Desmos, and I'm going to hit Functions. I'm on the Stats tab, and I find the NCR, and 8 was my N, 3 was my R. That means there's 56 different combinations. My next one on the notes is 11C5. Functions. We're at Stats, and we're going to go to NCR. 11 is the N. 5. Forgot what I was doing there for a second. 5 is the R. 462. 462. This last one, 4 combination 2, I'm going to show you using the TI so you know how to do it on this. You are going to hit 4, math, PRB, back to probability, and then you're going to choose option 3 for combination. Okay, so then you need to fill in the R, which is 2. So you will type in the number first, then the little symbol, then the R, and that's going to give you 6. A whopping 6 combinations. Cool. All right, so let's get into some word problems. A standard deck of 52 cards has 4 suits and 14 different cards in each suit. How many different 5-card hands are possible? All right, so this is a little wordy, and maybe for this particular question, we don't need all this information. There's 52 total cards, and we're drawing 5-card hands. This is a combination because it doesn't matter what order you are dealt those 5 cards. You're going to have the same cards in your hand regardless. You know that your N is 52. There's 52 total cards in the deck, 52 different possibilities for that particular event, that card to be dealt. And then we're making a combination, and I want a 5-card hand. So 52C5 is what I am trying to figure out. We can do the formula. We'd have 52 factorial divided by 5 factorial times 52 minus 5 factorial. So that would give us 52 factorial times 5 times, what's 52 minus 5? I hope you said 47. All right, so you can type that into the calculator if you want to. I'll show you how to do it again on the TI, and then we'll go back and do it on Desmos as well. So we've got 52, math, remember, PRB 4 is factorial, divided by 5, math, PRB 4, times 47, math, PRB 4. Okay, 2,598,960. That's quite a bit. Quite a few different combinations. Okay. No wonder the odds in Vegas are so bad. So let's type this into Desmos and see if we get the same thing. We're going to come here and we are going to go to Functions, and we're on Stats, Combinations. 52 is our N, 5 is our R, and there you go, 2,598,960. One of those options was much faster than the other, so choose wisely when you're doing your homework or doing your practice problems. There's absolutely nothing wrong with just typing this in the calculator, you guys. You don't have to do the formula every time. You may be asked on a test to show me that you can plug into the formula, but you know, when we get to the SOL, just type it in the calculator. That's going to be the name of the game here since we have such a short amount of time before the SOL. All right, so let's look at another example. A student must answer 4 out of 6 essays on an English test, and they may choose whichever ones they would like. How many different ways can a student choose those questions? Okay, what is the end value here? What's the total number of things in the pool? Did you say 6? We've got 6 total essays that we can answer, and we must answer 4. So that means that 4 must be the R. 6 combination 4. How many different ways can we choose those questions? Let's go ahead and type that into our calculator. 6 combination 4, and that got me 15. 15 different ways that the student can choose the question. Let's double check on Desmos. Functions, combination. We've got 6 essays. I have to pick 4, and you can see that my answer is 15. Awesome. Okay, so now we get a little more exciting. What happens if there is more than one condition placed on the grouping? When finding the number of ways, this is super important, you guys. That's why it's in a box. If you ever see something in a box, this is something that you need to commit to memory. When finding the number of ways both event A and event B can occur, and this is specific only to combinations, okay? This does not, don't bother with this with permutations. This is specific only to combinations. When finding the number of ways both event A and event B can occur, you will multiply the 2 combinations, or 3 or 4 combinations. It just depends on what you're being asked. Okay, in contrast, when you're finding the number of ways that either event A or event B can occur, you will, any guesses? I imagine all of you shouting, add, to yourself in front of your computer. You will add the 2 combinations. Okay, so let's take a look at exactly what I mean by that. Just remember, and means multiply, or means add. Okay, so how can we calculate out of the 2 million plus 5 card hands in the deck, how many 5 card hands are possible if all the cards are the same suit? In this case, 52C5 is not what we're going here. We're not trying to figure out how many 5 card hands are possible out of those 52 cards. We need to know that there are 4 suits in a 52 card deck. We're looking for how many 5 card hands are possible if all 5 cards are the same suit. So out of 4 suits, we're only dealing with 1. This is not our path. Instead, we know there's 4 suits. We want to pick one of them. And within that one suit that we have chosen, out of the 13 cards in that suit, we need 5 in our hand. And since this is an and problem, we're going to multiply them together. 4 combination 1 times 13 combination 5. I'll go ahead and do it on my good old-fashioned calculator. 14 math PRB 3 1 equals 14, good to know, times 13 math PRB 3 5. And we get 18,018. Well, that's a lot less than 2 million. And change. So 18,018. Okay, that was an and problem, so we will multiply. A basketball team consists of 2 centers, 5 forwards, and 4 guards. How many different ways can the coach select the starting lineup of 1 center and 2 forwards and 2 guards? So what are we going to do here, guys? Multiply. Yes, that's right, multiply. And we're going to have 3 different combinations that we have to multiply together. So for our center, we have 2 potential centers to pick, but we only want 1. So that's going to be 2C1, and, which is times. We've got 5 forwards, but we only want 2. So 5C2 times 4 potential guards to pick from, and we want 2 for our starting lineup. So 4C3. C2. We're going to multiply all that together. Let's do it on Desmos this time. Oh, not Spotify. Sorry, guys. You get a peek into my private life doing this. We're going to do this on Desmos. So we're going to do functions, NCR, our first combination, 2 and 1, okay, times 5 potential forwards, and we want to start 2. All right, times 4 potential guards, and we want to start 2. So 4 and 2. There's 120 different starting lineups that basketball coach has to pick from. That's a lot of potential. Let's check on the last problem here. Okay, last but not least, there are 12 boys and 14 girls in Mrs. Smith's math class. How many different ways can Mrs. Smith select a team of 3 students for a project if the team has 1 girl and 2 boys? Okay, so we need 3 total people. There's 12 boys and 14 girls, and we want 1 girl and 2 boys. So we are saying 12 combination 2, this is our potential boys on the team, and 14 combination 1. These are our potential girls on the team. Okay, 12C2 times 14C1. Let's go back to Desmos for that. I almost went to Spotify again. Oh, goodness. Okay, and we're going to go to functions. We're going to pick combination. 12 boys, we need 2. Close those parentheses. And same thing again, function. $14 and 1. Okay, there's 924 different teams that Mrs. Smith could make for her, let's just say, special math project. Okay, now let me ask you this. Let's say in a very twisted world, we can only choose one gender to be on this team. So there's 12 boys, there's 14 girls, and my team can be either 3 boys or 3 girls. How would I set that up? Because we're not dealing with multiplying anymore. We're using the word or, so that means we're dealing with addition. Yes, addition, you're right. So out of 12 boys, I would fill my team of 3, or out of 14 girls, I would fill my team of 3. I don't know what kind of twisted, non-equal opportunity math class Mrs. Smith is running, but for the sake of the problem, we're going to say it's the 50s. Okay, so it's 3 boys out of 12, or 3 girls out of 14. So let's go back to Desmos, and our last one we're going to run here, function combination 12 boys, we can take 3, or function combination 14 girls, and we can take 3. So now we've got 584 potential teams for Mrs. Smith's special secret math project, whatever it may be. Okay. All right, guys, so that's it for this video. Pause it, rewind it, watch it again if you have to. In your packet, you have a page to write down questions for anything that you do not understand. It looks like this. What questions do I still have about this section of the unit? Use this page, write things down. When you come to class, we will start with your questions.